Okay, so so here you go. So that's the history behind the charged particles that we know today: electron, proton, and neutron. And what we're going to do right now, we're going to do the actual simulation, the actual exercise. It's 2:02 right now. We have until 4:20 to do that. So it doesn't look like we'll be able to do the second exercise, but that's okay. We still can always do that later on. So let's get the virtual lab, Coulomb's law, the handout. Okay, no link there. So let's go to our link right in here. What you have to know that there is an electric force between electric charge. You have to know that there are three types of electric charge: positive, negative, and neutral. And there are electric forces between charges between particles that has an electric charge. Negative charge attracts positive, negative charge repels negative charge, and positive charge repel positive charge, right? That's something you must have seen in chemistry before. Okay, so let's go here. Yeah, that's not the slide I want. Let me get another one here. Okay, so here you go. You have positive charges, you can have, oh, you gotta put a negative charge here. Okay, you have negative charges and you have neutral charges. They're represented by the letter Q, and they're measured in terms of coulombs, okay? And we do have an electric force between those charges that works in a way similar to the gravitational force. The only difference is that we do not have negative masses and positive masses. We have only positive masses, right? And charges is a quantity completely different from a mass. And the difference lies in the fact that we have negative charges. We do not have negative masses. But when we put a negative charge next to a positive charge, they attract each other. That's Coulomb's law. When you put a positive charge next to a positive charge, they repel one another. The forces are the same, but the directions here is opposite. Okay? Here's that the force of 1 applied to 2. That's the force of charge 2 applied to charge 1. In the next video here, let me put here, some time ago I replaced the negative with the positive accidentally. That's why you're seeing positives there. Okay, here's my positive charge. Positive, let's see, it must be a negative charge. Yeah, that's a negative charge as well. Okay, so how does that force can be quantified? That force can be quantified according to Coulomb's law. Okay, and that is the equation for Coulomb's law. Is the constant K, charge 1, charge 2, divided by the distance between the charges square. The constant K is given by this value here. I do not know why I put this 2 here. It's not supposed to be there. That's the value of the constant K. It's a very high number, 10 to the 9, compared to the gravitational constant, big G. Let me go get my lab notes right here. Okay, that's the force of gravitation, gravitational attraction that you saw before. Here we have the constant big G. That's in vectorial format, okay? That's why I have this negative sign here. And here's the Coulomb's law, constant K. Okay, so this K is given by this large number, and this G is given, as you remember, is given by a very small number. I didn't put it here. Okay. Electric charge is a basic quantity. Protons and neutrons, we today know that are in the nucleus of the atom, and electrons surround the atomic nucleus. They orbit around the atomic nucleus. That's how we picture, that's a very good picture of the atom today. Every atom is made of protons and neutrons, and electrons surrounding the nucleus. Now, what dictates the chemical property of the atom is the number of protons in the nucleus. That's what dictates the chemical property of your atom. Okay, so let's go back to our virtual lab. Let's click here in the simulation. Loading macro scale. So what we're going to do, we're going to play with this law, with the Coulomb's law. We're going to see how it behaves. The same way that we saw how the gravitational force behaves. Okay? So this is the simulation. This simulation that we are going to do is very similar to the simulation that we did for gravitational force. One more thing that you have to know. Two more things that you have to know. Let's see. Lecture. Lab notes. Here you go, right in here. Okay. Let me get the value of the gravitational constant. Gravitational constant value, so we can compare constant value. Okay, 6.10 to minus 11. So I'm going to compare that side by side with that other value that you have. Here you go. Newtons per kilogram square per meter square. Here you go. Okay. So note that though this parameter is much larger than this one right in here. And there are these have consequences. It has very important consequences. These values here. Okay. Because my G is very small compared to my K parameter, when it comes to the microscopic world, the electric force is much larger than the gravitational force. That's what you have to know. So large that it can be neglected. And the mass of those particles are so small, the gravitational force can be neglected as well. In the microscopic world, it is as though those particles were massless. It is as though the mass of those particles can be neglected because their force, their gravitational attraction and their weight are very small. That's what you have to know. And that's what you have to believe. Okay? Because note C that the constant big G is much smaller than the constant K. This has a very important consequence. This has a very important consequence. It means that at the microscopic, it means two things. It means two things at the microscopic level. One, the gravitational attraction between electric charges is very small. And two, okay, notice that big G, it consists one more. Furthermore, because the masses of electrons and protons and atoms and molecules in general, are very small, their weight are very small as well. In other words, at the microscopic level, the electric force rules supreme. Okay? You can neglect the gravitational force. You may neglect the gravitational force. Just take into account the electric force, which is given by the Coulomb's law. Right? Remember, d is the distance between the electric charges. The format is very similar. We have a constant here. We have a constant here. Those constants have different units, by the way. Okay? If here is kilogram, here is going to be coulomb. They have different constants, different units. We have the source of the electric force here. We have the source of gravitational force here, which is the mass. The source of the electric force is the charge. We have a second electric charge here. We have a second mass here. And we have a distance square. We also have a distance square. Okay? Those are similarities. And there are similarities and there are distinctions between those two laws. So let's go back to our simulation. At this point in time, you may have it there. Let's go back to our Coulomb's law. Here you go. Simulation Coulomb. There's a mistake here apparently. Figure 9.5. So you mixed up the figures. What you position is supposed to come here, and vice versa. Okay, so there's a mistake here. There's a bunch of mistakes here. Okay. I put F sub C to distinguish, because he used F sub C here, you're supposed to be using F sub C here. Charges should be Q1 and Q2. You can, this link doesn't work. Okay, so macro scale. Yeah, see, they switched the figures. This figure is supposed to be here, and the other one here. Okay, so part one. Now let's go force versus mass. Versus mass? Versus electric charge. This is a mistake again. Another mistake. It's not versus mass. It's versus electric charge, okay? You can see there's a bunch of mistakes here, so we gotta be careful. We gotta be careful when we give those things away to the students. That's what I told my chair. And they're not doing much effort to correct all that stuff. I have to tell my students. Set the charge values for the two objects. Q1 for 4 microcoulombs, Q2 a negative 4 microcoulombs. Let's do that. At this point, you must have your simulation running. Everybody has the simulation running? Let me know that. Give me some feedback, please. Let me see. I'm going to call you one by one. Make sure you have the simulation running there. Bella, do you have your simulation running?
Yes.
Okay. Annabella? Do you have your simulation running? Okay, not yet, huh? Okay, let's go. I'm not gonna call everybody, but just call some of you. Jordan, do you have the simulation running?
Yes, I do.
Okay, one more. Shreya, do you have your simulation running?
Yep.
Okay, one more here. Alisa, do you have your simulation running?
Yeah.
Okay, good. So let's go ahead, set the values minus. Let's do according to the notes, right? This one should be plus plus, right? Plus 4 microcoulombs. Yeah, someone is asking a question? Nope. Okay, Q1 is positive, Q2 is negative. Let's see if that's what it is. Oh no, Q1 is negative, it's all the way around. Q1 is negative, Q2 is positive. According to the drawing, right? Here you go. According to the drawing, Q1 is negative, and let's put this way. So let's keep it minus 4, and that should be 4. Okay. What distance does he want? Line up the 0 centimeter mark of the ruler to the center of the first charge, and the 1.4 centimeter mark to the center of the second. Okay, so go ahead, move it to the right, to the left, and move it. Is that 1.4? He said. 1.4 right in here. Let's make sure 1.4. Yeah, 1.4 centimeter mark. That's right. Okay. Keep the charge for the first object. Oh, okay. Yeah, it's 4 microcoulombs. So that's what it's supposed to be. Keep the charge Q1. Let's invert the polarities. Yeah, 4. Okay, read the magnitude and direction of the electric force on Q2 by Q1. Okay, read the magnitude and direction of the electric force. Table, you gotta put the table here. We are going to create a table. You're gonna go to your spreadsheet. Let me get the spreadsheet that I did last semester. Hang in there. Bear with me momentarily. I want to make sure I didn't make any. On the fall of 2020, I did this experiment. Let me see if I kept my spreadsheets for that course. Directory course, Physics 122, lab spreadsheet must be this one here. Let's see, that's lab 4. No. Nope, not this one. Ohm's Law, lab 8. Let's see if it's this one here. Sheet 1. No, no. Yeah, it looks like we have to do from scratch. Looks like we have to do this spreadsheet from scratch. What about Ohm's Law? I have 4 other experiments, but I cannot find that for the Coulomb's Law. Student lab, lab spreadsheet. Let me see if it's in the notes, courses, contract, syllabus, student roster. Okay, we have to do that from scratch, otherwise I'm going to spend too much time here. If there is any adjustment that we have to do for the table, we'll do it. Summer 2. Okay, so let's go to my spreadsheet. Okay, I'm going to create a new spreadsheet. Coulomb's Law. Coulomb's Law. View, I'm going to freeze my panes. I like this feature of Excel. You can freeze the panes. And let me quit that. We don't need that for now. What we are going to do? we're going to set charge 2. We're going to change charge 2 and keep charge 1 constant, okay? But I'm going to create a, here you go, a column here with charge 1 anyway. Oh, I hate that. Q1. Here you go, good. Between parentheses. Go ahead. Format cell, subscript, okay? And then I'm going to create another column with Q2. Okay? Okay, so we want to force. Here you go, I'm gonna abbreviate that on 2 by 1. Force of 2 due to 1. That's what this notation means. Let me see if it's consistent with this other notation. Force of 2 due to 1. That's what I meant here, you know. Force is not exactly the same way that is defined there in the lab manual, but here you go, means force of charge 2 in charge 1. That's what this means. That's what my notation means. Here you go. Force of charge. You know, I'm going to do even better. Force of charge I on charge J. Put that between quotes so you know it's a name. Okay. You replace I with 1 and J with 2. You get this one here, right? That's how I use my notation. Here in this book, this notation force by, okay, it's all the way around. He's defining all the way around. Force on 2 due to 1. That's what the book is. Don't use 10 to the second. Just put newtons in there. Make my life simpler. On 2 by 1. And then you want the direction of this force. Direction of either positive or negative, okay? You put either positive or negative. Here you go. Direction of F2. Then you do the same for the other one. Okay, here you go. And I'm going to define here F of 2 in 1 means what? Means force in charge 2 by charge 1. It's a different definition that I made in my slides. Okay? And here we gotta do 1, 2. Here you go. Like that. I'm going to again, don't use 10 to minus 6 coulombs. And I gotta put another one. I gotta put Q2 here. I put only Q1. Let's put Q2. Okay. Oh, already did it. Oh, here you go. Here is going to be 4. Here you go. 4 divided by a million because it's micro. 1, 2, 3. 1, 2, 3. Okay. Like that. And here's going to be minus 4 divided by 1 million. 1, 2, 3, 1, 2, 3. I prefer the exponential for numbers less than 1,000. Okay, I prefer the scientific notation. Okay, so let's do that. Format, number, scientific, like that. Then we're gonna go down to 3, minus 4, minus 3, minus 2, minus 1, right? Oh, it's 3, not 2. Minus 4, minus 3, minus 2, should be minus 2. No, doesn't follow. Oh, what a shame. Supposed to. Minus 2, let's see if it does now. Sometimes it works, sometimes it doesn't work. What a shame. Minus 1. If the charge is 0, there is no force, then it becomes 1. Let's see if I can get it. Nope. Two. 3, 4, all the way up to 4. So what we're going to do, we are going to experiment with the Coulomb force. Oh boy. Let's go to our... Okay, take a look at the force. The force in charge 1 is to the right. I'll say it's positive. So it's 733.678 newtons. 733.678 newtons. The direction is positive. Put a positive sign here. Due to Newton's third law of motion, if the two objects interact with one another, the force of one is equal in magnitude but opposite in direction, right? See, the magnitude here is the same as this one, but the direction is opposite. So we put a negative. It's negative along the x-axis. Let me justify, center justify. And now I'm going to increase the value of charge increase. So I'm going to decrease. Increase, right? Because it's becoming less negative. Becoming less negative. So let's go minus 3 and here you go. Change it, the force changed, decreased. We are decreasing the value of the charge. The distance is kept constant, and the force should decrease as well in magnitude, 550 to 58. Okay, let's go next one, 2. Simulation, I'm going to put here side by side. We're going to go this way, okay, minus 2. 366,839. Minus 1, I can type it later on, right? Minus 1 is going to 183,419. 183,419. 0, charge is going to be 0 force. If the charge is neutral, the force is going to be 0. Electric force is going to be 0. 1 microcoulomb. 183, here you go, 419. The same as this one, but the sign now changes. It's positive. Oh, it's positive here, becomes negative because the charge Q changed sign, right? Here's the same thing. Negative, the force becomes positive. Oh, here the force is 0, so has no direction whatsoever. Here's 0. Alright, I'm gonna copy that and paste it here. And now I already know that a 2 is gonna be the same magnitude. Yeah, 366. Yeah, 839, right? 366, 839. Should be 550 next one. 550 to 58. And the next one should be 733. 733. The force on charge by charge 2. The force on charge 1 by charge 2 should be the same. It's just the direction that's opposite. Okay? So if you were to perform this experiment, we would perform it like that. This is not, again, this is not a real life experiment. If you were to perform this experiment, it would be in a different way. The procedure is different. This is more like for you to understand how the law works. In this experiment, how would you perform that in real life? In real life, we would use that same apparatus that you saw, that I showed to you for, I believe I showed that to you here, right? For the gravitational force in physics 1A, 120, okay? So that should be the Cavendish experiment using the torsional scale. Here you go, Cavendish, not Cavendish, sorry, it's the Coulomb experiment. The Cavendish experiment is for the gravitational force, okay? But let me see, doesn't look like the measures the electric force, June 17, let's see here, Coulomb experiment, 1785. Oh, it's different. But nowadays, he did in a different way. But nowadays we still. Oh, here you go. The torsional scale. Let's take a look. To measure the electric force. Did he use a torsional scale? Torsion balance. Yeah, he used the torsional balance. The same balance that Cavendish used to measure the gravitational constant big G. When he did that, let's see when he did that. Okay, he did that to provide the construction of a fort. Coulomb oversaw the construction and then he returned to front his health impaired by tropical ailments in Martinique. Would trouble him. Coulomb became interested in measuring the electric force between a small charged object and perfect a torsion balance. Which year was that? He didn't say. Went to Martinique. Okay, he stayed in Martinique until 1772, so he did that after 1772. Okay, so that would be, let me see if they have a better, let's take a look at YouTube, okay? Coulomb force experiment. Let's see if they have. Okay. Okay, let's take a look at this one. this equipment is rather expensive. Not every college has it. The only one that I know that has is Pierce College. Go.
This device is called a Coulomb apparatus. It measures static electric forces. The two spheres are charged electrically.
Okay. Those are the two spheres, right? Those are the two spheres that he's referring to. So he's charging it. He's charging now.
And they will repel each other.
So what he's doing, he's electrically charging this plate, and he's transferring the charges of the plate to the spheres. Okay? That's why he first rubbed it at the beginning. That's one.
The forces between these two balls causes the wire to twist.
Okay? That's the torsional scale, the wire that he's referring, That's the torsional scale that he's referring to. We had a wire for the gravitational force experiment as well, okay?
The water here in this container dampens out the oscillations.
Okay, nice. Okay, do you remember when I showed that in Physics 120, the Cavendish experiment? The guy was doing his laboratory and the ruler was oscillating back and forth. He could dump the oscillation, the back and forth oscillation, by dipping this, the ruler into water. That's what this guy is doing. That's a smart way of performing the experiment.
The stronger the force, the more the rope twists. There. A laser reflects on this tiny mirror.
Okay, it's very difficult to see this guy rotating, but now you will be able to see that there is a rotation because there is a laser incident in this mirror. Okay, do you see the laser right in here? If this mirror rotates, you will be able to see the beam of light moving sideways on the screen. That was going to show that to you.
And measures the twist. The laser's reflected light lands on this chart.
See that?
The
right
chart
in here.
measures how much twisting is going on.
The further away you put the screen, the more sensitive the experiment is. Initially start with the laser right here at zero, in the zero. By measuring this displacement of the laser beam, you know how many degrees the thread rotated. Okay? And from there you can calculate the force, the electric force.
Twice the force, twice the twist, twice the distance.
Okay, stable there.
All right, let's get started. The balls are initially uncharged, and so the chart over...
So that's the real life way of performing the experiment. Okay? What you saw right there in the simulation is not real life, it's more like a way for you to understand how the Coulomb's law work.
Here is reading about 0.
Okay? The spheres are uncharged right now.
Initially, the balls are 10 centimeters away.
Okay?
Both of them get charged, and the rope begins to twist.
You can hardly see that. It's easier to see the laser. The angle is so small that's difficult to see it. The twist of the wire is so small that's difficult to see it.
Now, to what distance should I move the balls apart in order to measure half the original force? You see, the force is proportional to the square of the distance. This means that the original force was proportional to 1 over 10 squared, or 100. The second force
There's centimeters, right?
1 over radical 2 times 10 squared, which is 14 squared. That means 1
14
over
centimeters.
200, half as much.
Because the force, the static force goes down is the square of the distance. To get half of the force, you do not have to double the distance. No. You have to do a little bit less. You know, a little bit. You have to do square root of 2 of the distance. So from 10 centimeters, he's going to move like 14 centimeters away.
The correct distance is 14, because 14 is radical 2 times 10.
I like this ruler that he made. It's pretty handy, you know, very smart. I think I know this guy. I met him at one of those meetings. He teaches physics at high school. I guess that's him. He's president of the Southern California Medical Association of Physics Teachers.
At about 14 centimeters away, you get half of the force. This is because 14 is radical 2 times 10.
So now we have,
Coulomb's law, forces decreases the square of the distance.
you have half of the deflection.
Right, whole new experiment. The balls are all charged up, and so over here we're getting a reading of about 14. Now I have this device which will take half of the charge off this ball. Now what will the reading be?
Should decrease.
Over here on the chart, we see the reading settling.
Little by little. It doesn't answer right away. It's not instantaneous, okay? So it was 14, now it's 7. Approximately 7.
As much. From this experiment, we discovered that the force is proportionate to the quantity of charge. Now there's 2 charges, so we say it's proportional to the product of those 2 quantities. We also discovered earlier that it was inversely proportional to the square of the distance, and that's Coulomb's law.
Okay. So that's how we do an actual experiment. And let's move it back here. Let's see if I can. They have a better. Yeah. Okay. Let's continue here with our simulation, right? So what is going to ask now? Go back. We got our table. Examine carefully the data recorded in table 1 and answer the following questions. What relationship can you establish between the magnitude of the electric force Q1 by Q2 and the magnitude of the electric? They are equal. Okay? Just like Newton's third law of motion. When 2 objects interact, the magnitude of the force of 1 in 2 is equal to the magnitude of the force of 2 in 1. Based on the direction of the electrical force, what relationship can you establish about the nature of the electrical force between 2 charged objects? Okay? The force is attractive when the charges are opposite. The force is repulsive when the charges have the same sign. The sign of the charges. If the object is not charged, then there is no electric force whatsoever. Now here we go, referring to magnitude of the electric force. We know that, here you go, Q1, force of Q1 by Q2 is equal, let's see, Q2 by Q1, the magnitude, we're talking about the magnitude here. Okay. Yeah, he didn't put enough space here, did he? I hate that. Yeah, not good, not good. Let's put a space here. Here. Okay. That's the relationship KQ1, Q2 divided by D square. Okay. So what we are going to do now, he's going to ask you to plot this graph against Q2. If you plot against Q2, you should get a straight line. Okay, let's do that. Use Excel in the data you record in table 1. Make a graph for the electric force on Q1 and determine the equation for the linear graph. Okay, so here we go. Make a graph of the electric force on Q1 by Q2. Let's go Q1 by Q2. This one here. This one and against Q2, right? Yeah. No, by Q2. Yeah, that's the one you want. Let's insert chart. Oh, there's something wrong here. Let me see. Yeah. But he's asking the magnitude, right? He's asking the magnitude. Let's take a look here again. Let's make sure he asked the right thing. Scientific notation. Let's make sure the force. Keep the charge. Read the magnitude. He's asking the magnitude. Okay? Because he's asking and he asked the magnitude, we log the magnitude. Because of that, we get that funny graph like that. Okay? But if you were to write the force with the actual sign, let me get this thing here in a different format. Tick marks, label, number. Here you go. Scientifics, decimal place. Here you go. Better. Chart title, no chart title. I don't like chart title. Shrink the graph. Don't forget to put the labels, right? The better way of doing this graph is to put the actual signs here in the force. That's a better way. So since the direction is negative, let's put the negative here on this one. Let's put the negative here on this one. And then you're going to get a real straight line. Get the negative sign. Similarly, we're going to put the negative signs here, which means negative direction along the x-axis. And now that we put the right sign in the numbers, we get a real straight line. Okay? Force along the y-axis, charge along the x-axis. Right, chart design, add chart element, axis title, primary horizontal, primary vertical. Here you go. Primary horizontal, put it closer, let's see, right here. It's gonna be what, Q2? Yeah, Q2, because that's the one that's varying, right? Put the unit of Q2 there. Don't forget to put subscript. Take your time to do that when you do that at home. You're doing that in groups, so you can divide the tasks among yourselves. You know, make it sure it looks nice. The font, I'm gonna italicize my font. I didn't italicize, yeah, I did italicize, good. And here we're gonna put the force. Force in 1/2, right? In 1/2, here. We are going to subscript gonna subscript it, font. Like that. Oh, don't forget to put the units. I forgot to put the units there. Okay, here you go. like that. Why so large? 10 plus? Strange. 10. Let's put just 10. Why did 10 plus there? Yeah, like that. We can adjust the axis. I think there's too much blank space here. Let's cut down all the way down to 5, not 6. Axis option. So minus 5 to 5. And the major units, we're going to do like in 1 unit. Oh, too much, too close. I don't like it. Okay. How are you going to do that? 2.5. Yeah, let's try 2.5. Nope. Yeah, they're too close to one another here. This one is okay. Can I do better than that? Yeah, it looks like we should leave at 6. It doesn't look good. Even though there's a big space there, we cannot do much about that, right? And then we put the major ticks every 2 units. Okay? Charge and force. Can you do better? Let's see. 4.5. Let's see. 1, 1.5, 3. I think we can go to 4.5. Let's do 4.5 here. Let's see if we can do that. 4.5 instead. I don't like there's too much space here. Axis option. 4.5. 4.5. Okay, and then we're going to get it 1.5. Let's see. And then we increase, put one more decimal place there so we can see all the decimals that we need to see. Okay, now it looks better, right? 0, minus 1.5, minus 3, minus 4.5. We eliminate that big blank space that we had before. Okay, and now what else do we have to do? We have to put a regression equation there. That's gonna ask, right? You go. Keep the charge. Let's see, this one go down, go down, go down. Make a graph for the and determine the equation for the linear graph. Okay, here you go. Regression equation, add trend line. Display equation chart, display R square. I want to see more decimal places here. See, this number is very small, right? Let's see if I can get this formatted line label. I'm going to do scientific. Yeah, now I have more, right? But what about this R square? This R square usually is not 1, it's actually 1. Yeah, this one seems to be 1, right? Yeah, this one is. In real life, we do not get R square equal to 1. In real life, we get the R square less than 1. But what I want is this slope right here. Note that the intercept is very small. The intercept is supposed to be very small. Okay, and on the graph paper provided, right? Graphing page. If it's not a linear, okay, you did get finding the constant k. Let's find the constant k from the graph. Okay, let's do that. And before we go to our Let's finish that so we can go to our break. Let's get this one here. I'm going to get this, my favorite software. It's coming on board, coming in. We're going to calculate the value. Here we go, internal energy, Coulomb's law. Okay? So we know that Coulomb's law is what? K, Q1, Q2 divided by D squared. I'm going to put the D squared downstairs here instead. Okay? Q2. So this is the slope of my graph. This is supposed to be the slope of my graph, okay? And the slope that I got, get the right units. Don't forget to get the right units. The slope that I got in the graph, 183 times 10 to the 8. 1.83. 1.83 times 10 to the 8. And then we gotta write down the units. The units is gonna be what? It's gonna be newtons, right? Is the rise divided by the run divided by Coulomb. Everything right? Let's see if everything is right. Take a look. Newtons, rise divided by the run. Okay, that's the slope. And he wants us to, using this equation for the values of Q2 and D, find the value for the constant K. He wants the constant K. Okay, here you go. Constant K. We are going to use the slope in this equation, and we have to use the other values that we know. What's the value for D? The value for D, do you remember, was 1.4, right? 1.4 centimeters. Yeah, 1.4 centimeters, but we want to change it to meters. 1.4 centimeters is 1 centimeters is 100 of a meter. So we put everything in the right unit. Charge Q1 is equal to what? 4 microcoulombs. Micro is 10 to minus 6. So, like that. And we can substitute that here. We can substitute Q1 here. If I did everything right, I should get the expected value. Expand. Yeah, almost, see? Almost 9. 9 times 10 to the 9. It's not exactly 9, but it's close enough. That's what we should expect. 310 right now. Any questions about that? So let's have our break. Lecture notes, lab notes, break again. Let's see here. Part 1. Okay. Break till 3:25 p.m. Well, there you go. Okay, we're done with the first part. And now we're going to do the second part. Okay. And what we did first. In the first part, let's document what we did there. Lab notes. In the first part, The first part, we varied the value of one of the charges and determined the force. We confirmed that there is a linear relationship between them. Okay? Now in this part 2, what we are going to do, we are going to vary D. Okay?
Professor, you're not sharing your screen.
Oh, I'm sorry. Thank you. Let's go. Here you go. In the first part, we vary one of the charges and determine the forces. Now we confirm that there is a linear relationship between them. In the second part, we will vary the distance between the charges and determine the force. According to Coulomb's law, we should determine that the relation is the inverse, that the relation is the inverse of the square of the distance. Okay, so let's go back here to our right here. Part 2, set the charge of the two objects to 4 microcoulombs. Okay, let's go back. 4 microcoulombs. Oh yeah, they're both 4 microcoulombs now. We don't have to worry about that. Set the distance between the two charges to 2 centimeters. So we gotta go 2 centimeters. And read the magnitude of the electric force. Record the value in table 2. Now we're gonna do the same table, in a different way, by the way. The way we are going to do it, just like we did for the gravitational force. Okay, a second table. Here you go. That's gonna be D. And then we're gonna do a second column here, X. Do the second column as being X, okay? There's a reason for that. And then the force, you log it here. Don't forget to put the units. Use all units, preferably in the SI unit. Here you go. X is gonna have, I'm gonna tell you what X is very soon. And the unit of force, you should know what the unit of force. I'm gonna center justify them all. What else? Nope, not this one. I want this one right in here. 2, 4, 6, 8, and 10 centimeters. 2, 4, 6, 8, and 10. And by the way, just like I said, put that in meters. So divide by 100. Yeah, I gotta put the equal sign, otherwise it's going to complain to you, right? Here you go. And just change here 2. It's easier to do something like that. 4, 6, 8, and 10. I'm gonna tell you very soon what X is, but if you remember the simulation of the gravitational force, you should know that's gonna be the inverse of the square of the distance. Make your table looks nice. Go like that. Like that. What is the force? The force is 359.502. 359.502. I want to shrink this table and share it with this simulation. We're going to increase the distance to 4 centimeters. You go 89,876. 6 centimeters. 39,945. 945. Oh, 945. That's good. Next is 8 centimeters. 22,469.4 newtons. And the last one, 14,380. Okay. Going back, we got everything that we want. Don't forget it's 4 microcoulombs, right? So we can document those values here as well. Q, put that below, Q. Oh boy, I hate that. Yeah. 4, 1, 2, 3, 4, 5, 6 microcoulomb. What he wants to do, he wants to plot, use Excel, make a graph of F coulomb force against D. Based on what you see in the graph, discuss briefly the relationship. The graph linear or not linear. You see inverse relationship between, okay, so let's do the graph. D and force. Insert chart right here. Shrink it. Here you go. Right? You go ahead and add chart elements. Primary horizontal, primary vertical. Put D here. Put the units. Put the force here. Put the units. Okay, this relationship, you can see that's inverse of the square of inverse. The relationship is the inverse, right? You do not know it's the inverse of the square. You do not know it's, inverse of the third power. You do not know it's the inverse of the first power, but you know that's the inverse. One way to find out what the relationship is just by, try to get the display equation in the chart, and then you try all those options that you have in Excel. You can try the exponential and and you display the equation chart, display the R² value on chart, okay? And keep on trying. Which one do you think is going to, I know, oh gosh, I know from fact that the power should fit better, right? See that? We are getting the inverse of the square for the D. And I even get the coefficient here in front of it. Okay? So that's one of the graphs that you're going to plot, but then you're going to do the other graph. Here you go. What we're going to do, we are going to plot against the inverse of the square of the distance. We're going to linearize this graph. So that's why I put that second value right here is going to be 1 divided by this guy here square. Okay, so, and now we plot, just like we did for the gravitational force simulation. Force and the inverse of the square of the distance, insert, plot, here you go. Now we managed to linearize it. Shrink the graph. Let's see what they ask. Here you go. If you are sure you found the correct relation, step 5. Calculate x and record the values in the appropriate column in table 2. Make a sketch. What are the slope and vertical intercept of the graph? Okay, you gotta put the trend line there. Trend line. Display, here you go. You insert, add chart elements, error bars, axis title. Okay, here you go. The square, don't forget to put the units here in between parentheses. We are going to font, superscript, bold faced, force, put the units there between parentheses, bold face. That's the type of thing that you have to do whenever you are going to publish a paper. Okay, and we got a slope and intercept. Okay, and what else that you want? Finding the charge. Okay, we want to find the charge. Using the relation you established for step 5 and the slope of your linear, I find the charge. That's the calculated value of Q agrees with Q for microcoulomb. Okay, so let's do it. I got my Coulomb's law. Let's see, part 1. Part 1. Here you go, part 1. Part 2. I'm going to use exactly the same equation. And how we're going to do that? Okay, this equation has been linearized, right? So the slope now is going to be given by K, Q1, Q2. That is the slope. And what I'm getting for the slope, go. I'm getting 0.1438. 0.1438. The slope has a unit of newtons divided by what? 1 divided by meter square. Don't forget to simplify this equation. Don't leave this way, okay? Simplify it, you get Newton meter squared. That's the unit for the slope. And now that you have the unit for the slope, now that you have the value for the slope, you can calculate what's going to be Q1 and Q2. Don't forget that Q1 is equal to Q2. Here you go. Or let's say Q2 is equal to Q1, right? Here you go. And my K we found before is 9 times 10 to the 9, you put all the units in there. Newton what? Per Coulomb square? Yeah, per Coulomb square. Now, Newton meter square per Coulomb square. Yeah, meter square per Coulomb square. That's the value of K. We solve for Q1. We take the square root of both sides and calculate. Let's see, it doesn't calculate this way. Let's see if we can do better than that. We gotta pass this Coulomb to the other side. It's really annoying that he does that. Now he didn't used to do something like that. I need to apply square root to those guys, and now we should get the right result. Expand. Okay, you gotta expand that as well. Calculate. Yeah, go. Oh, it doesn't expand this one. Oh, what a shame. Let's try it. Let's see, collect factor. Yeah, now it should simplify. Yep, it did simplify. Gotta do this additional step, unfortunately. And so for the charge, okay, we got it, 3.9972. Okay, so save as. Let's see what else he asked. I believe we finished. Okay, if not, what was the group determine? Why not? Did we get, let's see. Yeah, microcoulombs for 3.99 times 10 to minus 6 coulombs. Okay. We 3:45 right now. We have half an hour more to go. Basically, that's all I want to do. We couldn't do the other second experiment. Let's go to our syllabus before we finish here. Okay, we will have to leave this one for the next meeting. We must, must do at least 2 experiments, right? At a certain point in time, so we finish everything on time during the semester. Here you go. I am updating my syllabus here for the lab. That's going to be version number 02. You cannot do that in half an hour. You cannot do this one in half an hour, okay? Let me see everybody's still here. So let's save it to PDF format. Okay, Annabella, are you still there?
Mm-hmm.
Okay, good. Any questions, Annabella?
No.
Okay. Sarah?
Here.
Okay, any questions?
No.
Okay. Carly?
Yes.
Okay, Bella, right? Should ask for Bella as well. Bella, are you there?
Yes.
Okay. Mahedi?
I'm here.
Okay. Wesley? Feel free to ask any questions if you have. Are you there, Wesley? Let's see. No, Wesley's not here, huh? Oh, I gotta think what I'm gonna do about him. What about Ada? Is Ada there? Let's see. Ada, I see Ada listed here, but she's not answering. I don't see Wesley. Okay, Wesley, no, I'm gonna put 0 like that. No, O. Oh, for no answer. I'm gonna put no answer for Ada. Okay, Jordan, are you there?
Yes.
Okay, next is Donica. Are you there, Donica?
Yes, I'm here.
Okay, Shagar.
I'm here.
Good. Daniela.
I'm here.
Okay, Dior.
I'm here.
Next, Shreya.
Here.
Peter. Peter. Let's see. He was here before. Huh? Hey, wait a minute. Okay, I'm listening. Oh boy, I'm doing all the way around. Okay, that's Wesley. Okay, I'm doing the wrong spot here. Okay, Wesley here. Let's see, Annabella. Okay, you are there. Let's see. Let's do the four. Oh my gosh, I messed up. See that? No answer. Was putting on the 14th. Okay, don't think there was a problem here, right? Now, Donica, Shagar, Daniela, Dior, okay, Shreya's there, right? And Peter's not here. Ana Ponce, are you there, Ana?
I'm here.
Okay, Kaylee?
I'm here.
Okay, next, Alisa?
Here.
Okay, and Jasmine Tobar?
I'm here.
Okay, the only one that didn't answer was Ada. Ada, are you there, Ada? I see you listed here, but I don't hear you answer me. Okay, that's the only one who's not answering me. Okay, any questions? So I'm gonna start posting the homework for chapter 15. Again, for the exam, for the first exam is only chapter 13 and 14. I'm gonna post the recordings for chapter 15. We are gonna leave chapter 15 for the second exam. And before the end of this week, I post also the notes for the chapter 16. There will, just work out, just use the notes of the labs to help you with the material for the lecture, okay? Because I'm gonna compress the video for the chapter 15 because I already did this video for the lab. Much of the material that was used here in this lab applies also to the lecture material of chapter 15. Okay, so we're finishing a little bit earlier here, and if you don't have any questions, let's see. Can you, Annabella? Can you allow multiple attempts to check our homework problem? Right now you do have multiple attempts, okay, Annabella? I didn't change anything. So,
Professor?
yeah.
When I checked today, there isn't multiple attempts. It doesn't let you check your work.
Did you check? Did you call Connect to ask them? Because remember last time I showed to you all that here you go. Let's go back there. I showed to you that it's set up for multiple attempts for both homework, Annabella. You're having this problem for both homework.
Answer the question, but it doesn't let me like check it if I got it right or not. Just like has me submit it at the very end.
Uh-huh. So at this point, I cannot change the policies, okay? But I can do that for the future homework. Once you start the homework, I cannot change the policies. He doesn't let me. He go. That's the no time printing questions are ordered. Let's see. Unlimited attempts are allowed, okay? But on each new attempt, you have to start over. Okay, I didn't change that, and I cannot change anymore because we folks already. Let me show you. Let me see if I can change. Most likely I can't because you already have started your homework. And so, but for the future, I'm gonna have that in mind. Let's see, review and assign. Expand advanced settings, right here. No time limit. Printing is allowed. Questions are ordered. Not password protected. Given for accurate. Unlimited attempts are allowed. Okay. So start over. Let's see if I can do it. Revise the previous attempt. Allow students to revise their previous attempt even if manual grading. For each attempt of the first. Let's see if he lets me do that. So the problem is that you have to start over, right? That's the problem, right? You can do new attempts, but you have to start over from zero, okay? So I believe I have to check this one here. Let me see, apply to this assignment only. I don't think he's gonna let me do that. Your assignment has been updated. Oh, he let it. He let me do that. Oh, interesting. Okay, so it looks like he let me do that. Now check if you can do that. Allow for steady attempts. Anything else? Let me see, review and assign. Okay. It's already assigned. I don't think I need to assign it. Can we allow multiple attempts to check our homework problems before we submit the assignment? Yeah, so it's already allowed for multiple attempts. The only problem is that you have to start all over again. Hopefully it has changed. Let me save and exit. Okay, let's see here. Homework chapter 13. Let's see if it changed. It saved the policies. Here we go. Printing is allowed. On each students revise their previous attempts. I do not know what that means. Students are not allowed to revise their previous attempts if manual grading questions are not yet graded. Okay, that's manual grading questions. We don't have manual grading questions, so you don't have to worry about that. There is no score deduction for taking new attempts. Okay. Accented character, corrected space, question points values are shown. How are we going to take the exam? Are we logging into Zoom? No, you're not logging into Zoom, okay? This is an asynchronous course. I mentioned that before, right? The exam, I'm going to, let me write that down here. Lecture lab notes, exam. For the exam, I will give you, for the exam, you will have 1 hour and 15 minutes to do the exam. Within a 24 hours window. Okay? There is no, because this is an asynchronous course. There is no need for you to log into Zoom. Okay? That's because it's an asynchronous course. If you're not an asynchronous, I cannot. I would be able to do that. But because it's asynchronous, I cannot demand that from you. Okay? Don't forget, partial exam is 1 hour and 15 minutes. Partial exams is 1 hour 15 minutes long. Final exam is 2 hours long.
How long is the partial exams? I mean, how many questions?
Well, it's going to be adjusted. The length of the exam is going to be adjusted according to the time. I gotta check how many I did for Physics 120. I don't recall right now. I believe I was doing like 20 questions for the final exam and maybe 15 questions for the first exam. I gotta check what I did before. Okay. Do you have who took Physics 120 with me? My lecture. Whoever took Physics 120 with me, yeah, whoever took Physics 120 with me may remember what I did then. And will the exam be on Background Connect? Yes, all exams will be on Background Connect. Yeah, that's right. But you don't have to log into Zoom. You do on your own. You're not, you're not allowed to have anybody help from outside, but you can have your notes to do the exam. Open note, open book. Okay. Yeah, okay, good. Thank you, Annabella. Yeah, that's what I saw, 10 to 15 questions, right? And the final exam was like a 20, right, Annabella? I believe the final
Yeah, I
exam
think it
was,
was like,
yeah, I think it was 20 questions that I did for the final exam. I'm gonna look there in Connect. It has to be a little bit longer because you have more time. That's why there will be more questions there. Go, let's put it partial exams. 10 to 15 questions. Final exam, approximately 20 questions. Like that. And you have, only 1 hour and 15 minutes to do it, but you have a 24-hour window to fit your 1 hour and 15 minutes there. Okay? Any more questions? Okay, so we can finish here. I will upload this video there. Don't forget to check the other videos that I have as well. So hopefully it will help you for the homework and the exam, okay? By the way, some of the videos that I'm uploading there is, there are some things that were not done well in the book, especially in the kinetic theory of gases. And I mentioned there, okay, the way that the book derived the equations for the kinetic theory is not correct. And this is a mistake that other books has made as well. And I found one specific book that did everything right in the way that it's supposed to be done. Every time that I find a mistake, I mention that in my videos, okay? Okay, let's stop sharing here, and if you don't have any more questions, we can finish it now. I have office hours at 4:20, and if you don't hang around, see you next time on Wednesday. You too. Have a good day for the rest of your week as well.